Hello everyone, this is Sri Guru over here. Welcome back to my YouTube channel. Today we are going to discuss the classification of semiconductors. Semiconductors are classified into two groups. The first one is intrinsic semiconductor. Intrinsic semiconductor means it is a pure semiconductor. And the second one is extrinsic semiconductor. Extrinsic semiconductor is nothing but it is a impure semiconductor. Further, extrinsic semiconductor is divided into two groups. The first one is N-type semiconductor and the second one is a P-type semiconductor. Look at the first properties of intrinsic semiconductor. As I said, a pure semiconductor is called intrinsic semiconductor. The second property is it has a thermally generated current. That means by using the thermal energy or heat energy, it produces the current. They have 4 electrons in the outermost orbit of the atoms, and the atoms are held together by covalent bonds. We will see in the diagram next. Electrons and holes both are charge carriers, that is number density of electrons in the covalent bond which is equal to number density of holes in the valence bond. The effective current I in the semiconductor is the sum of electric current IE and hole current IH. I is equals to IE plus IH. By combines together, we will get the total effective current in the semiconductor. Look at the structure of silicon or germanium atom. This is a two-dimensional diagram. As we know that silicon and germaniums are having the 4 free electrons in the outermost orbit, and that 4 electrons is shared by its neighboring atom as is shown in the figure. As you can see here, the 4 electrons here, they are sharing with its neighboring atoms. Each atom is shared by 2 electrons to its neighboring atom with a covalent bond. The 2 and 2 and 2 and 2, that become the 4. This is how the crystal structure is there. If we apply electric current to the intrinsic semiconductor as shown in the figure, here we are using a cross-sectional area, and this is a semiconductor and the length of the semiconductor is L and the cross-section area is A, and we have applied the potential difference across the semiconductor. As we apply potential difference across the semiconductor, the electric field is set up inside the semiconductor. The electrons should move opposite to the direction of electric field from this end to this end, and the holes should move from this end to this end. And the total current we can calculate by using the relation between current and the drift velocity. That is I is equals to NEAVD. As we discussed earlier, the total current in the intrinsic semiconductor should be sum of hole current plus electronic current. That is I is equals to AE into bracket NH into VH plus NE into VE, where this A is a cross-sectional area and E is a charge of an electron, and NH is a number density of holes, and VH is a drift velocity of hole, and this NE is representing number density of electron and VE is a drift velocity of electron. Further, the conductivity of the semiconductor, intrinsic semiconductor, is given by sigma is equals to E into bracket NH into mu H plus NE into mu E, where this NH is number density of holes and mu H is mobility of hole. Here also Ne is a number density of electrons and mu E is a mobility of electrons. Further, the limitations of developing a pure semiconductor based devices. What are the limitations of intrinsic semiconductors? In a pure semiconductor at room temperature, the number of intrinsic charge carriers, that is electrons and holes, is very small. That is why the pure semiconductor is a low conductivity material. The second limitation is, in a pure semiconductor, the intrinsic charge carriers are always produced due to the breakage of the covalent bonds by the virtue of thermal motion. Hence, enough flexibility is not available to control their number of pure semiconductor. Third limitation is, in pure semiconductor, the number of electrons is always equal to the number of holes. It is never possible in a pure semiconductor to have either large number of conductivity electrons only or large number of conductivity holes only. That's why pure semiconductor is not much of use. These are the limitations of intrinsic semiconductor. So that to increase the conductivity, we are adding the impurities to intrinsic semiconductor, and that the process of adding the impurity is called doping. Doping is a process of adding the desirable impurity atoms to a pure semiconductor to modify its property in the controlled manner. The impurity atoms added are called dopant. The impurity added may be 1 part per million. That means very small amount of impurity we are adding to the impure semiconductor. There is a limitations, or we have to follow a proper procedure to increase the conductivity of the intrinsic semiconductor. What type of dopant we should use to increase the conductivity? Look at the first one. The number of dopant atom should take the position of the semiconductor atom in the lattice. As we add the dopant to the intrinsic semiconductor, it should replace the intrinsic semiconductor atom in that place. It should fit it. The second one is, the presence of the dopant atom should not destroy the crystal structure. That means, as we add the dopant to the intrinsic semiconductor, it should not damage the lattice structure in such a way that it should fit in that position. The size of the dopant atom should almost be same as that of the crystal atom. The size of the pure semiconductor atom and the dopant size of the atom should be equal. The next one is, the concentration of the dopant atom should not be large. That means not more than 1% of the crystal atom we should add. It is to be noted that the doping of the semiconductor increases its electrical conductivity to a greater extent. By the different methods we are doping. The first one is, add the impurity atoms in the melt of the semiconductor, or heat the crystalline semiconductor in an atmosphere containing dopant atoms or molecules so that the lattice diffuse into the semiconductor. Third one is, implant dopant atom by bombarding the semiconductor with their ions. We will discuss the extrinsic semiconductors in the next video. Thank you for watching my video. Don't forget to like and share and subscribe. Thank you.